So we have our first actual remote video conference lecture. Hooray. This is Joel Fish at the Institute, who will provide oracles in between. Howdy. Good. All right. So I've run down sort of the general form of moduli spaces that I sort of roughly threw at you last time. And I'm gonna, that's gonna be sort of my mantra. That's sort of almost sort of the form in which I'm gonna mostly think about moduli spaces. As sort of the zero set of a Cauchy-Riemann operator quotiented by some usually finite dimensional compact, non-compact Lie group, and then something still pretty vague, some broken and nodal curves that somehow get glued into that quotient space. So the analytically nice thing here is that this Cauchy-Riemann operator will see as a Fredholm operator in pretty much every case. Well, or can be made one. If you take a base space of maps, maybe with marked points, we fix some kind of homotopy class. If there's boundaries, we might have to fix Lagrangian boundary conditions. And we may allow ourselves to vary the surface of the domain as well as the marked points in some space. And we might also, allow the actual target space to vary in a finite dimensional family. And so these automorphisms here, do act on that base space mostly by reparametrizing the map, where phi could map different surfaces biholomorphically to each other. Both are in this family. And if there's marked points, it has to do something similar with the marked points, or it has to fix the marked points. Either. And if we ask phi to fix the marked points here, then we usually don't let them run in this space. But those are all subtleties. So there are a bunch of confusions that will sort of come up, and that I think are also sort of part of some sort of pretty foundational confusions in the field. Difference being between this automorphism group here and stabilizer groups of specific domains, or stabilizer groups of maps. So I'm going to try and be very, very careful with my language here. So let's see. First of all, so these underlying domains, and I'm often going to think of marked points as part of the domain, are called stable. If the stabilizer subgroup of this automorphism group is finite. So those would be biholomorphisms of the surface itself. And if there's marked points, they have to fix all the marked points. So each one of them. So we'll often work with such finite stabilizers, but the basic example that we had, the sphere with one marked point, has a four-dimensional stabilizer. Right? So that's not a stable domain.
And the sphere with three marked points?
The sphere with three marked points is stable, exactly. And the sphere with three marked points is also kind of really the only, or one of the very, very few cases where I believe one can globally make the setup with a finite automorphism group. In fact, in that, like the empty automorphism group. because you can simply once and for all fix the surface and fix the marked points, and then you just have to quotient by, you know, whatever stabilizer that was. You know, you would think that when you have 4 marked points or 5, you could do something similar. But they're really, you know, either the marked points are going to move or the J is going to move. You know, the little complex structure can change. And, you know, locally you can fix things to get a nice Fredholm description. But if you want to make this sort of globally, global nice description that's sort of prepared to have this gluing construction, then you really do need to change the parameterizations of your surface in between. So, sort of, that's the reason that I say this automorphism group is pretty much never finite dimensional, never discrete. It's because once you have more marked points, you really do want to quotient out again. So by, you know, different choices of sort of local slices in your space of marked points on a sphere. But that's like super metaphysical. So when we get there, we can talk about that some more. So for now, right, so our domains may or may not be stable. Our maps, however, will always be stable. So a stable map now is, you know, usually a holomorphic map on a domain that, well, if the domain is stable, then your map is also stable automatically. But if the domain is unstable, you're going to look at the stabilizer of the map, which are the automorphisms that fix the domain and that also fix the map. So if that's finite, we call U a stable map. And just to drive this home, a stable curve, then for me at least, would be the quotient of the map modulo automorphisms, meaning in this case it would be U mod the stabilizer of U. So some people, I believe, call domains modulo automorphisms then stable domains. So stable curves. So, and that, you know, I'm going to try and call the surfaces always like surfaces or domains of Riemann surface, and, you know, curves for me will always be unparameterized holomorphic maps. Right, and so, well, we'll usually, you know, look at somewhat non-trivial homotopy classes. However, there's some notion of finite energy, and so, you know, the maps not being constant but having finite energy will, in all cases I know, guarantee stability for the maps. So that gives us some hope that, right, so if this d-bar operator cuts something out nicely, transversely, yeah, then, and we're quotienting here by something that only has finite stabilizers, we do kind of expect to see an orbifold-like thing, or, you know, global quotient. That's not too bad. So that's one of the reasons we expect regularization to work.
I'm a little bit confused.
Okay.
So if
Yeah.
we have like a holomorphic two-sphere wrapping a non-trivial cycle, then shouldn't all of the PSL2C of that two-sphere be part of the stabilizer of that map?
Well,
or fix the map point-wise?
if I fix Well, no, because they don't. So if you have a 2-to-1 cover, say, of from the sphere to the sphere, well, all right. First of all, let's say if U is just the identity map from the sphere to the sphere, right? And then what you're asking here for is a phi, so that identity composed with phi is the identity.
Okay.
So that's only the identity, right?
Okay.
So if you now replace U by a 2-to-1 cover, you'll see, I think, just 2 elements in the stabilizer.
All right.
So that's the important thing. The reparameterization has to take U to U. Right? So, and I guess when you have a 2-to-1 cover, and you fix a point in the image, there's only 2 pre-images, and so phi has to permute those 2.
Yeah. So it's always like deck transform.
Right.
That's why it's fine.
Yes.
Or if U is constant, I think. Right.
Right. If U is constant, then this becomes big, but it isn't, because we're usually working with non-trivial homotopy classes. Yeah. Good. So, all right. So here's the zoology of what kind of domains and what kind of automorphisms there are, and then some rough pictures of what happens when you add the nodal curves. So let's see. Genus 0 Gromov-Witten, we simply fix the sphere with the standard complex structure, and there will be some extra mark points flying around. The easiest way to think of the automorphism group is really just to take all automorphisms of the sphere, and they will move the mark points around. And then in the compactification, I hope so there's blue dots, so this is the case where you have 3 mark points, so those will somehow distribute themselves over various spheres, and there's there's some pink nodes between the spheres. So, and just so I give that disclosure at some point. There are cases, I believe, where the space of the non-nodal curves is actually the empty set, and for a certain homotopy class, there only are nodal solutions. So in no sense is this an actual compactification. So the d bar, the 0 set of the Cauchy-Riemann operator minus mod the automorphisms does not have to be a dense subset. So every time I say compactification, you should really sort of put quotation marks around that.
Maybe we should accept that compactification means a nicely defined compact space with nice properties that contains the original set, which could possibly be empty.
Exactly. Yeah. So so really one should say Gromov compactification. That's because Gromov found that nice set. Yeah. Right. When I say compactification, they're always compact. So that at least is true. Good. So higher genus Gromov-Witten, in the main component, you can think of this as fixing the surface, letting the complex structure vary, and letting mark points fly around. So then you have to quotient by biholomorphisms that take one j to another j. And then 2 things can happen. So sort of interesting nodes can form, that actually, so this is a degeneration, or these 2 are degenerations here that actually come from j changing drastically. Right? There are some lengths here that go to 0 on the surface. And these sphere bubbles here really, there's no way in which you can reasonably, up to isomorphisms, make this degeneration by degenerating J. However, these occur from the maps doing something funky. So these bubble spheres here come from the gradient of the maps blowing up, and I'm then sort of forcefully just rescaling my maps, and and sort of that's really sort of more a choice, of how I describe the extra elements in this space, as spheres attached to these surfaces. And this is again, there's a lot of metaphysics here. How exactly you do, you sort of describe limits. It gets even more interesting when you throw marked points in. So, but just as a general sort of visual. So so here this was also for the genus 0. This was all sphere bubbling that sort of in some sense all comes from gradient blow-ups in the maps. When we go to higher genus, we can get the complex structures degenerating, and we can still have sphere bubbling. In Hamiltonian Fleur theory, what we're looking at is the domain is now non-compact. It's a cylinder, with the induced complex structure from taking this as a quotient of C. Now the actual automorphism group here, of course, is R times S1. However, we usually break this S1 symmetry with a Hamiltonian perturbation of the d-bar operator. So what we quotient out really is just shifts in the R direction. And very similar in Lagrangian Fleur, your domain is now a strip, and so that really now just has the R symmetry. And so in both of these cases, one additional non-compactness is now a breaking, where if you think of the domain, let's see here. If you think of a domain here just as a cylinder, breaking one sees really by kind of blobs of energy of the curve going off to different ends, separating. So, well, one could stay, in finite area, and one might go off one end or the other end. And so, we sort of shift them to sort of keep each of the blobs inside, and then sort of one of the blobs of energy you'll see on one cylinder, the other you'll see on another cylinder. And somewhere in between there's very, very little energy, and that then means that your curve has to be very close to a Hamiltonian orbit, or in Lagrangian Fleur, two blobs are on. So these are now strips with boundary conditions on Lagrangians. In Lagrangian Fleur, you have to be close to an intersection point of your Lagrangians. And so that's what I would call breaking. Where really in breaking, energies shift apart infinitely, whereas in bubbling, energy concentrates at a point. This is also nothing that I'm somehow forcing with degenerating the complex structure. That just stays the same. All right. Then there's an extra. So in Hamiltonian Fleur, the only other thing that can happen is sphere bubbling. And then in Lagrangian Fleur, we have some extra fun, because if I get bubbling near the boundary, the things that bubble off can be spheres or disks, depending on how fast they bubble off. So one extra type of bubbling there. All right. So now going to possibly less known, but probably things that you've heard the slogans of. So when somebody talks to you about A infinity, Fukaya, something, there are different things. There's an algebra that's associated to a single Lagrangian, and there's a category where you have all kinds of Lagrangians. So for the algebra, what you're looking at are simply disks with marked points on them, and the entire boundary of the disk has to go to one fixed Lagrangian. So, yeah. Here, I've put a whole lot of marked points on this, so in some sense, there might actually be. So this bubble here with 3 marked points could actually be represented by a constant disk, and just the 3 marked points having run together, which we don't like. We don't want the marked points to cluster in the limit. So we do several blow-ups. One if the maps diverge, and one if marked points run together. This could also be one of those bubbles. Here, there's just 1 marked point on this, so that was a case where definitely the map diverged. So this would be a real bubble with some energy. So disk bubbles here are the most interesting thing, but you always also have sphere bubbles. And again, so here, well, if you put exactly 3 marked points on this, then, yes, you can think of all your marked disks as just, the disk with 3 fixed marked points on it. But if you have more or less marked points, you'll have to deal with some automorphisms. Either move marked points around, or, that fix 1 or 2 marked points. All right, so the A infinity category starts with something pretty similar. You have marked points on the boundary of a disk, but we're now not going to think of them as marked points. We're taking them out of the disk and thinking of our disk as a domain with strip-like ends. So now there's a non-compactness in my domain. I still should, allow myself to move those marked points around. So those are, I can think of that as automorphisms of the disk. And now sort of different things can happen. One is that still, some of those marked points could run together. And in this world of sort of strip-like ends, that looks a little bit like, so this kind of node here, I'm now going to think of as an infinite strip in between. And so there's, some breaking occurring on the level of the domain here. That's sort of being forced by moving the marked points. So that's one type. Then also, because I now have a non-compact domain here, I can get energy running out to infinity on any one of those strips. So that's a case of breaking on the level of maps. And finally, there's always bubbling, so I can have all kinds of disk bubbles on the boundary and also sphere bubbles in the interior. So here I now have 4 kinds of breakings and bubblings to deal with. So finally, more horror cabinet. So the rough buzz idea, so if you hear the buzzword contact homology, what you should think of are sort of similar, you can think of this as now a closed Riemann surface with some marked points on it, but we're going to take the marked points out, so this becomes a non-compact surface. And in contact homology, we allow ourselves something called positive punctures and just take one negative puncture.
Usually it's the other way around.
Oh, goodness.
So the
Yes.
the basic picture would be
We
genus
call
0
them-
and one positive puncture.
Right, oh goodness. Yes, because you go up, huh? But then you always draw the pictures the other way around.
Well, no, so well, no. Well, I don't know what you mean by
Yeah.
the other way around.
Well,
When the-
I
when
mean,
the
you
arc
usually
when the
draw
arc
these
coordinate is
pictures,
going
right?
Plus infinity.
Yes,
When the arc coordinate is going to plus infinity, that's a positive puncture.
right,
And so the most basic version of context homology is one positive puncture.
yeah. Oh, so you draw this picture the other way around.
Yeah.
I see, okay.
Because up on the page is the arc coordinate getting positive.
Yes, okay. Sorry, so you should flip this entire
Yeah,
picture.
yeah.
All pictures should get flipped.
Also, the one positive, restricting
Yeah.
to one positive puncture only makes sense when the genus is 0.
Right, So wait, but hold on, so there's no contact homology with genus?
Well, there is, but then it doesn't make any sense to
doesn't make-
restrict the number of positive punctures.
Okay, so then
Genus,
contact,
it's symplectic field theory or ECH. I mean,
so that we should call, okay, so that we should call, good, I'm glad I have the experts here. Let's see. So let's say genus 0.
Sure.
Right. So that's a real mistake. The other one is just language. So, right. I guess I think of these things as machines, you know, and machines get some number of inputs on top and spit something out on the bottom. I guess you guys
I do also, but I think if the input is on the top,
as on the top.
and has one of them, and then a bunch of things come out.
Oh, okay. Now I'm getting my algebra.
instead of an L infinity algebra.
Of course. No, wait. Oh, and I'm thinking too much of A infinity context. Okay. Oh, geez. Okay. So, so one in
We could just call this intact homology.
intact. So one input, K outputs. Okay. Good. I've gotten A infinity too much. Yeah, that's maybe the interesting thing. I'll say a little bit about A infinity later on. In A infinity cases, you have K inputs and one output. So, anyways, so, okay, so the big thing that changes here is that now, I'm not talking about automorphisms anymore here. This is about what is my symplectic manifold. So my symplectic manifold here became non-compact. And so now I get yet another type of degeneration where some part of my curves likes to run to plus or minus infinity. And well, one part that certainly runs there is, you know, the positive punctures run to plus infinity, the negative run towards negative infinity. They are forced to have some nice asymptotics there. But what can also happen is that the sort of interesting parts or energy of my curve, you know, runs towards plus and minus infinity, and so then I get something called buildings, where I get sort of several copies of my target manifold, and you know, in each floor there is some kind of non-trivial curve.
Which I think is very similar to breaking.
Right. Yes. Well, you can reformulate Floer breaking in these terms, right? But you can't go the other way. Yes. Yeah. And this is now wrong because there are no. There are no nodes that will form in this setup.
That's form, I think.
These are all punctured spheres. Only sphere bubbles, I would say.
Sphere bubbles in contact.
Yeah. Oh, right. And no sphere bubbles because usually these are exact.
Usually
That's
always.
why it's exact.
Right. So in this case, actually, breaking is everything that happens. So that's pretty nice. One would think that it shouldn't be so hard to define contact homology now. The bad thing that happens here are these, sort of dotted lines. Those are kind of zero.
I don't see why you can't have nodes in general. Like, why can't a punctured sphere split along a node into two things?
Oh. So we're saying something like.
So points on two adjacent legs.
The maximum principle.
Right, because you only have one.
You're right. Okay.
And
if there's only one positive end.
Right.
You're right. Okay. Good.
Yeah. Good.
I don't understand what just happened.
Yeah. Maybe you don't need to. The experts have concurred that because of the restrictions here, there are some analytic principles that say you cannot have parts of your curves that only have a positive end.
I mean, you can worry about a node form.
But yes.
And something else can over there. But this is actually not allowed because this over here violates the maximum principle.
You could have finite energy planes, though.
Come again?
You could have finite energy planes.
Right. That's sort of encompassed in the buildings part, in the breaking into buildings.
But she doesn't have a picture of what a finite energy plane would look like in that.
No.
It looks like they're all like pairs of pants or maybe suggestive of cylinders.
Right. Well, okay. I can't draw everything. Okay. So, yes. I'm going to add this to the notes drawn nicely. Yeah. Let me not try to do this on the fly. Right. So everything we restricted out here, if we're going to full symplectic field theory, we let all of that happen. So we let genus happen, any number of inputs, any number of outputs. And now our symplectic manifold usually has sort of a negative end that looks like R minus times a contact manifold, a positive end that looks like R plus times a contact manifold, and some part in between. That's called then a symplectic cobordism, which is why that whole thing is called symplectic field theory. And then this is the case where one could also decide that one wants to actually degenerate the symplectic manifold. There could be a nice cut across here, and you might want to sort of stretch that. And when you do that, no matter whether you stretch here or not, there's multiple things can happen. As a part of your buildings can run off to plus infinity, they can run off to minus infinity, or when you're stretching, you can get bits and pieces in the middle, and then you have sort of all buildings with various levels. Some levels live in y plus only, some levels live in y minus only, some levels will sort of live essentially in this sort of infinitely stretched middle bit, and then there's some sort of non-trivial cobordism types that I think will just happen in one level each. So lots of interesting limits there. Now also we can get nodes because that maximum principle, there might be another end, a plus infinity part, so you don't actually get forced into maximum. And because these symplectic manifolds will, there's something non-trivial happening in the middle, they might not be exact, so the sphere bubbles might happen. All right, so you might think that this is the most general thing to look at, but in fact we have no boundary at all here. So relative SFT is maybe not really a theory that completely exists. So it certainly doesn't exist in this full generality where I would now take punctured Riemann surfaces with boundary. So add possible boundaries here, non-compact, compact. And then you have to throw some appropriate Lagrangian submanifolds into your symplectic manifold and ask for boundary conditions on that. So then you get buildings again. Now your nodes are either in the interior or on the boundary. And similarly, you can have sphere bubbles or disk bubbles. And I think this is really an area where the abundance of bubbles here, in particular the boundary nodes and disk bubbles, really make it pretty unclear what the algebraic formulation should be. So I think there's very little question of how this analysis is going to work. Once we can do all the other analyses, we can throw them together and describe all this. But we don't even really know how to organize outcomes in the end. All right. So that's pretty much all the kinds of curves you might ever want to count or regularize. Well, and then some people like to throw Morse trajectories in between or make some other constraints that your curves have to go through certain hypersurfaces or all kinds of extra fun. Right. So, so these are the moduli spaces, and what we want to do with them is, we like to regularize them in some sense. Question?
Yeah, for the last one, the relative symplectic.
Yeah.
Is there any restraint on what the boundary of such a thing would be?
Of the domain?
Or the boundary of the domain.
No, you can just I mean, you essentially, you take a punctured Riemann surface and you just cut any open set out.
Okay.
The question might be where the boundary's going, with the answer being a Legendrian knot across R, or a Lagrangian cobordism between Legendrian knots.
And that's what it ends up looking like.
Right, so the input is you have a contact manifold with the Legendrian knot, or a symplectic cobordism between contact manifolds together with a Lagrangian cobordism between Legendrian knots. And then the Riemann surface is the boundary on this Lagrangian.
So that's what you end up with, or that's what you start with?
Well, that's sort of what you want to somehow count.
Okay.
So it's sort of a generalization of the previous case where you had holomorphic disks with boundary and a Lagrangian, which was further up from the slide somewhere. And now the Lagrangian is becoming non-compact with sort of asymptotic to Legendrian semi-contact manifold.
Right, so pictorially, what the extra condition here is that your map will have to take, the boundary to some Lagrangians, and what Michael just said is that the Lagrangians sort of tend to become sort of nice and straight out towards infinity, where it's R times a Legendrian knot, and in the cobordism they could do something more funky. So the Lagrangian I would think of as sort of part of the data of the domain, of the target. Okay. Good. So, right. So the game in all this sort of pseudoholomorphic curve business is we write down these already pretty weird sets of curves. Then we'd like to do something to give them sort of a nice structure, and then we're going to get some algebra out of it. And eventually we're going to use that algebra to prove something about the geometry of our symplectic manifolds. It's a pretty long process. Right? So, and there's sort of different types of regularization that one needs. The one I talked a bit about is sort of the basic Gromov-Witten one, where you'd really kind of like to just have, in some sense, a fundamental class in the right, dimension on your actual space of curves. Because if we had that, we could then take, cohomology classes on my symplectic manifold. So there's M bar, right, is the moduli space, and M is the symplectic manifold. So what I have here is then there will be these evaluation maps that take curves and evaluate them at the ith marked point. And so if my cohomology class is wedged to the right degree, I can pull them all back, hopefully, to my moduli space. And if that has a fundamental class, I ought to be able to integrate that. Or I could think of pushing this one forward and then, pairing downstairs. But this is usually how people write this. And the geometric idea here is that these alphas are dual, Poincare dual to some submanifolds, and in some sense this should be the number of curves then through all these submanifolds. Alright, so that really is sort of the symplectic analog of algebraic geometric curve counting. Except we get rational answers sometimes, so or no answers. Right, so that seems pretty obscure. You want a homology class on some, pretty funky space. The story in Flow theories is usually a bit easier. Really, we really just want to count, and we want to know that our counts give us sort of things that are equivalent in some sense. So we're usually only interested in the 0 and 1-dimensional parts of our moduli spaces. We throw everything else out. And we'd like the 1-dimensional part to be a cobordism between sort of broken points in the 0-dimensional thing. So there's usually some type of fiber product that's some sort of finite data. In this case, when you have Flow trajectories, you look at what the ends limit to, and this fiber product just says, the ends match, so I could stack them on top of each other. So, what good is this? So, just having sort of the 0-dimensional part actually be a compact 0 manifold allows me to count curves and use that to define a differential. And then this cobordism, allows me to deduce that the differential squared is 0, because differential squared has something to do with these pairs, and the 0 comes from knowing that the number of ends of a one manifold with signs is 0. So that's the regularization that you need to get going in flow theories. And most of the other theories have versions that work similarly. So certainly, contact homology and SFT, and also the infinity categories, you can phrase really as just looking at 0 and one-dimensional parts of the manifolds, where you'd like the boundary of the one-dimensional part to be some kind of discrete fiber product of the zero-dimensional things. And then again, the story is that counting the zero-dimensional things gives you some type of operation on some kind of algebra. And the one-dimensional cobordism proves a relation for this operation, which some people like to write as the master equation. There's always some composition of sort of twice this, that's 0. It's usually then not a differential, but something more complicated. Right. So, except when you do the infinity algebra Fukaya style, you do want to do something more Gromov-Witten type like. However, so in Gromov-Witten we expected our moduli spaces to sort of become smooth manifolds or branched manifolds without boundary. For the disks, there is no way that we're going to get these things without boundary, so our moduli spaces we expect to have boundary. So the kind of structure that we have here are a bunch of evaluation maps from the moduli space with subscript k now means k plus 1 marked points. And right, so at all of these points I can evaluate, I actually get points on L, on the Lagrangian, because my marked points were on the boundary. And these disks can split in various ways. There's going to be 0 will be on one of them, and some of the marked points will be on one disk, some will be on the other. So this distribution here you think of as some kind of fiber product again of these moduli spaces with different numbers of marked points. So, in an ideal world, we would make all these moduli spaces here smooth manifolds. So let's pretend that for a moment. Then, the way that we would define the infinity algebra would be to somehow work on some chain complex on the Lagrangian. And then I have k inputs of chains. What I'd like to do is pull back these chains to my moduli space, intersect them all on there. Hope that maybe I'm allowed to wiggle them a little so that they intersect transversely, and I get a chain of the right dimension here. And then I would take the last remaining evaluation map and map that chain up here to L. So that then is a map from a fairly decent triangulated space to L, so that itself should be a chain again. And then we'd like, summing over all these, we'd like to get the master equation again from the one-dimensional, from this boundary. Right, so there's no 0 and one-dimensional things now, just from this sort of boundary property. Right, so here I'm not really sure what precise claim I should make in terms of regularization. Somehow, clearly, even assuming that these are manifolds with this boundary, I then had to, wave my hands and say, what do I do with these chains? I know of a way to make this utterly rigorous by sort of adding Morse flow lines and then pulling this whole setup back into the world where you're just interested in 0 and 1 manifolds. If you want to understand this fairly complicated setup, I think, in Fukaya or no Ota, where you really have to sweat a little about how you can deal with these spaces of chains here. But it's, I think, visually the easier thing is to actually draw nodal disks rather than have Morse flow lines fly around everywhere. And so this is going to be beyond the scope of me talking about regularization. So mainly I'm going to talk about making a fundamental class in a case where we don't even have boundary. And I'll say a little bit about making sense of boundaries. Okay, so that's the giant task. So are we doomed? Well, not so much. So next thing is I want to sort of go through a couple of nice analytic features of our moduli spaces that all say, look, they could look really, really fuzzy and really singular, and there's all these complicated pictures that happen, but really there's sort of nice analytic description of them in many places. However, I do need to start with a warning that I think I talked last semester about, and I'm going to talk about this more when we get to polyfolds. For now, if you haven't seen this, the challenge would be to find some topology on a space of maps in which this kind of action, the reparameterization, is differentiable, even at any one point. So my claim is that you're probably not going to find anything as long as B is an infinite, and as long as B is actually a Banach space or manifold of maps, not a finite dimensional one. So something like CK maps will not work, nor any kind of Sobolev space. The only place where this is differentiable is when B is a finite dimensional submanifold of smooth maps. Well, the only place where it is smooth, let me be. So if you want it to be, I think, no wait, I think you need it in the smooth ones even to be differentiable. The reason is essentially that you can get these things differentiable if you think of this as mapping from C2 to C1. And so the nice thing about infinity is that infinity minus 1 is still infinity, so shifts are not going to matter anymore. So that's the bad news. And if you haven't seen this, that's a nice exercise to try and calculate what the differential is. You'll actually get something meaningful at a dense subset, but then you should ask yourself whether, go back to your definition of differentiability, that you need to check sort of a superlinear approximation, and that fails. So a lot of bad stuff. So we have a non-differentiable action here, so really a priori you wouldn't expect any good structure of the quotient. However, there actually are something called local slices. So a local slice means an open set in here that is homeomorphic to a finite quotient of a Banach space. So something like a local orbifold chart. So this finite set will usually be a stabilizer group. And so the puzzle is, what is the Banach space? And how do I get this homeomorphism here? So let's see. Let me go to my example of curves with one mark point. So there's u of infinity here. The rest is the image of my curve. And yeah, now I could reparameterize u, right? That's a map from the sphere by this whole four-dimensional group, yeah, of maps that fix infinity. So I would like to fix that parameterization near my fixed map u. So I'm going to take u, well, curly u here as some neighborhood of little u. So I'm going to take the, be very anal here. I'm going to take the classes curly v, which have a representative that is, say, C too close to my fixed curve. Well, then I have to. Well, this should be an open set in here, yeah, depending, of course, on the topology that I've put on B. So, actually, this is the time, right? I think C1 should be enough. So, yeah.
Do you mean V and B mod odd?
V curly. This V?
Yeah, you're saying U equals some set of.
Yes,
some
of
subset
equivalence classes. Oh, right, yes, sorry, indeed. Good, yeah, otherwise that was entirely nonsensical. Yeah. Good. Oops. Endless fun here. So, right. So I'm also going to find some nice points. Oh, in fact, I'm going to parameterize u a priori so that at some nice points, for example, the point 0 and point 1, du is actually surjective. At 0 and at 1, I'd like that to be, no, not surjective, sorry, I'd like that to be rank 2, so injective. So that's going to map to some points here, and so the image of the differential is actually going to have a two-dimensional, give me a two-dimensional tangent plane to my curve here. You know, this curve looks awfully smooth. You know, the image of u could be sort of a very, you know, folded up, weird singular thing. But I have these nice two-dimensional things here, and I'm just going to take some small pieces of hypersurface that go directly through the image point here and are perpendicular to those surfaces. So H0 and H1, I'm going to take in M so that they intersect transversely the image of u, and well, ideally u is injective, and then the only intersection point is that point, but yeah, sometimes these will be several points. So good. So now these two conditions here are going to tell me something about the nearby curves. Right? So my nearby map V now, right, will be C0 close to u, which means it better still intersect those two hypersurfaces. And the reason I asked it to be C1 close is that I wanted it to also intersect, you know, transversely. So each of these hypersurfaces will still transversely intersect my slightly, you know, different curves. And, well, the parameterization is also close to u, so there will be some point near 0 that maps to this hypersurface H0. And in the case of 1, there will be some C1 near 1. Right? But there's no way that I could guarantee that V exactly, yeah, intersects there. However, right, now that I have some parameterization of V, I could change the parameterization of V, yeah, and just move these 2 points exactly to 0 and 1. And that's a unique choice there, because, you know, my symmetry group is exactly fixed by, you know, 3 points. So this orbit then is also represented by V composed with little phi. Let me call this V prime. And V prime now has the nice properties that it actually maps 0 and 1 to my hypersurface. So my my Banach space now is, well, let me not say this right, so U, so this neighborhood, well, I just made sort of a one-to-one map, but let's take this way, will be the good maps in, oops, the good maps in all of U. Well, so let me call this some neighborhood of U. So this will be in my big space B, but I've added an extra condition, namely that V prime of 0 is in H0 and V prime of 1 is in H1. So dimension-wise, I wanted to divide by a 4-dimensional group. Instead, I added 2 conditions that cut down by 2 dimensions. Because the intersections are there, there's no question, and just asking the intersection to be at a specific point in the sphere cuts the dimension down by 2. So, and right, what I essentially created here was the map that took the sort of equivalence class here to the specific representative. And then obviously every specific representative here gives you an equivalence class, and check that that is, in this case, actually a bijection, unless U itself had some symmetries. And so then I would pick up some finite group here that I would still have to, quotient out by. So that's the good news. Right. So, well, this is of course an extra step here, right? This here, and I would say one can sort of think of as a Banach manifold, and then you'd have to, make some local charts to give it, structure of a Banach space. So, but what that suspiciously looks like is a Banach manifold chart for this quotient space. So this is the time when, you get really excited. And then maybe you get overly excited and think that since you have charts, that means your quotient space is a Banach manifold. But that then is the point in time when you should check 2 things. First, you should check that your quotient space is still Hausdorff, because that does not follow from having charts. And quotients of Hausdorff topologies can be non-Hausdorff. And we've made those mistakes. The bigger problem here, and you can make that space Hausdorff in most cases. The bigger problem is that you also should check your transition maps. And here the problem is, let's see. So if I have 2 of these open sets, and homeomorphisms to sets given by some intersection conditions, with different hypersurfaces, then I'm going to get an interesting W maybe. So I'm going to get an interesting transition map here. Where I have to reparameterize my map in this space. Of course, only if it's right. V here needs to be in this and in U12. Right? So I want to think about the overlap. So I have to reparameterize V so that it goes to the right. This guy goes through the right hypersurfaces at 0 and 1 for the untildified chart, but now I need it for the other hypersurfaces. So I guess what's going on here is that V again will map some Z0 and Z1 to these hypersurfaces, and the phi V is going to be given by mapping 0 and 1 to these points. So the reason I say phi sub V is that it really is given by the places where V intersects the hypersurfaces. And so, if phi was not depend on V, then there's a very good chance that this map was differentiable. However, phi does vary with V, and the lack of differentiability here comes from variations in this automorphism group. So the only way to sort of write this analytically is a composition, that goes through this non-differentiable action. So that's where differentiability likes to fail. All right. So we'll sort of, at some point I'm going to say, hopefully a little bit about Bernd Siebert's approach to regularizing. And I believe he really sort of tries to formalizes, in what sense there are local slices and in what sense the transition maps fail to be differentiable. And in some level, this quotient space has sort of a weak Banach manifold structure, and then there's a question whether you can work with that. Talk about sections over that. So. Bad news, good news, not so good news. Better news. So we had a local slice, and we can now use this local slice to actually describe our moduli space locally as a Fredholm section, right? Because we simply can take, so let's say there's open subsets of this space, which will now be homeomorphic to zero sets of a section that's essentially the D-bar operator. And, except now our base space is going to be this curly U. So, well, I keep writing curly E for the D-bar operator. So, whenever there's a curly E and a D-bar operator, you should just imagine that curly E to be whatever fibers you need so that the D-bar operator goes there. So this curly U is now going to be maps in our initial base space. Oh, and now I should not call them U, because U was our center point. Right, so this here will be a neighborhood of a fixed holomorphic curve U. Okay. So I'm going to take a local slice near that. So that's going to be this local slice. And then I'm going to look at my d-bar operator only on the local slice. And that should, cut out the right neighborhood here. Well, maybe up to, another finite stabilizer group. So that's good news. However, it is a local description. So, remember the regularization theorem in finite dimensions, right? I mumbled that you could generalize that to Fredholm sections. So one should, 5 years ago I thought, this is all going to work by simply using the regularization theorem in these local charts and then somehow gluing together the regularized moduli spaces. But, over the last 5 years I've learned that this regularization theorem really only makes sense when your unperturbed zero set is compact. Right? However, here we're trying to do something local. This is an open neighborhood. This is not going to be compact. So running the regularization theorem in something non-compact gives you all kinds of ambiguities. And so then the problem really is to sort of glue these ambiguities together. So, but that kind of, on some level, what this property here allows you to do is to sort of take these, global analytic differentiability problems and turn them into more topological problems of how to glue finite dimensional stuff or finite, chains of some kind of pieces of fundamental class together. So you could turn your analytic problems in 1 and 2 prime into topological problems. And that would be a fantastic approach if these topological problems were not incredibly subtle to deal with. So subtle that a lot of them we kind of just never really saw. And a lot of them also I still don't really understand why they are there and what the right way is to deal with them. So there's going to be a horror cabinet of the topological problems that you pick up when you do this. So, essentially, sort of, again, preview some regularization approaches, go this way and try to deal with the topological problems. Some will just sort of say, I don't want to go there, I'm just going to deal with the analytic problems. And I think there's also one that is, I believe, sort of the Siebert type approach that sort of tries to sort of stay in the middle and deals with the analytic problems where they're fairly easy to deal with, in the hope that that makes the topological problems not too bad. So, plenty of philosophy there. So what I was talking about right now is the abstract regularization. All of this abstract regularization sort of needs to deal with, or that uses this local Fredholm description. That uses the d-bar operator restricted to local slices. Because really you have to quotient by the automorphism group, and abstractly there's no hope for equivariant transversality. So that forces us abstract approaches to work with the d-bar operator on local slices. And the geometric regularizations, of which variant J is one. There's others that I would call geometric. On some level, this could be the definition of geometric regularizations, is that it manages to use the global Fredholm description. That uses the d-bar operator, on this entire space of maps curly B, and then manages to find equivariant perturbations. But my mantra is that to get equivariant transversality, you need some geometric understanding, and some kind of magic needs to come in to get that. So, and this here will require usually some geometry, some geometric control. All right, so that's the aside, and next week I'm going to go on to talking about not just this piece of the moduli space, but the broken stuff that we get to add. It's going to be more good news from now on analytically.